Shaw's algorithm and factoring 35. So they had a good description about how they actually came up with different tweaks to do, and then they divided the 3 tweaks into 3 different exercises: 2A, 2B, and 2C. So essentially, the main focus of 2A was nothing but to implement a circuit which had this following state transformations to come. So for this, I will just just give a minute. It's no, never mind. We'll just start it over here then. Yeah, so we have the picture over here. So essentially, this was the circuit, and just remember we have a control qubit over here always, and then this is marked at T1, and this is marked as T0 following this. So if we just, and it's given that for a transformation, all the control qubits should be equal to 1. So we have numbered them all as 1. And if we, and we'll just write it as T1 here and T2 over here, sorry, T0 over here. So if we see that T1 remains the same and T0 is having a transformation when C equals to 1, and even, and so like the basic thing is like we need to derive the relation between C, T1 and T0. So if I just talk about C and T0, you just need to see that in all the cases control qubit is 1, and every time there is a transformation in this particular qubit, which is T0. So this becomes 1, this 1 becomes 0, and then 0 becomes 1, and then 1 becomes 0. So which, and when it's, and all these transformations are happening when control qubit all are equal to 1. So essentially we can say that your T0 is basically at the end it's controlled from C qubit. So that means there is an C0 gate which is acting between both of them, which means that whenever my control qubit is 1, my state change, there's a state change for T0 qubit. So we have a like the relation between control qubit and T0, and now we need to derive something which involves T1 also. So if we see like in the cases where T1 is having a state transformation, this is one case, and this is another case where your this particular qubit, I'll take a different color, yeah, where your this particular qubit is having a transformation. Like in this 0 remains 0, and this 0 becomes 1, and this also 1 remains 1. But in this case over here, your 1 is actually having a change to 0. So which basically, so there's only a state transformation in T0 in these two particular cases. And why so it's happening? It's because in these two cases only, your T0 value is equal to 1. And even your control qubit value is equal to 1, which basically means that only when your control qubit value is 1 and your T0 value is 1, there is a change in T1. If you see in the other rest all cases, like if you see the first case, your C is 1, but your T0 is 0. So T1 remains 0 itself. In this particular case, your C value is 1, your T value T0 is 1, and that's why your 0 is becoming 1 over here. And if we see in the third case, your C value is 1, and but your T0 value is 0. So essentially your T1 remains as 1 and there isn't a change. And if you see over here, your C value is 1 and your what if you say the T0 value is 1. So there is a transformation from 1 to 0 over here, which basically means your T1 is basically controlled by T0, C and T0. So that means, and how it's controlled, it's that when both C, when T0 and your C are 1, this thing particular changes. So what conclusion we can draw, that we can put a Toffoli gate where your T0 and your C will act as the control qubit and your T1 essentially will be the target qubit. So if we come down to the exercise of over here, so if I put a control Toffoli gate over here where my first two bits parameters, they represent both the target, the control qubit. So over here, my T0 and control qubit, which is just one, so we denote it as C0, are my control qubit, and the third parameter, which is nothing but the target qubit, is T1. So for this transformation is this, and the second relation which we found that was that there is a relation of C0 between control qubit and T0, where your T0 is the control target qubit and where your C0 is the control qubit. So that's how we do the derivation. And then if we run it, this is the circuit if we obtain for this all the state transformation. And if we so this is how we solve 2A, and essentially coming down to 2B. So if we have the same, we take it, we have a same approach over here. So yeah, so if we see over here, first thing which we should notice is how is the state evolving. Like, so same thing, this is T0 and this is T1, and I have my control, which is again all 1 over here. So if we see T0 0 0, so 1 1, so and there's a 0 0, and then there is a 1 1. So basically if you see, your T0 state is not changing, like in all the 4 cases. So that means there isn't any transformation in the T0 qubit. So we'll just keep that particular thing aside, and now we observe T1. So it's 0 over here, and then it's 1 over here, it's 0 over here, and it's 1 over here, it's 1 over here, and it's 0 over here, and then it's 1 over here, and it's 0 over here. So we can see in all the 4 cases your T1 state is changing, and on all the 4 cases our control qubit is also 1. So if we see the relation between them, it can be directly a C0 operation, because when the control qubit is 1, acting like is, and so when T1 is the target, so when C equals 1, there is always a state transformation in T1, like your 0 becomes 1 over here, and then is again 0 becomes 1 over here, your 1 becomes 0 over here, and the same thing, 1 becomes 0 over here. So essentially you can say that only your T1 and C are involved in the quantum circuit, and whereas since there isn't any state transformation in T0, so you can just keep that aside and need not include it. So if you see in the exercise directly, so essentially we just place C0 between C0 and T1, where your control qubit is C and your target qubit is T1. And then if we run it, like this is the circuit which you obtain, and this is the answer for this particular circuit, like this particular table, like the transformation which they talk about. And this was like the easiest exercise of all, because if you see, like there isn't any state transformation in any of the circuits, so we can just like you need not do any operations. So the other thing which you should remember is that, like, since you're using CX and CCX, it's better to write this particular dot decompose statement, which which basically means it will again decompose all your gates which are there, like Scafuli gate and the C0 gate, into its more elementary set of gates. And so that will be like it for the transpilation purpose that can be done. So this was the exercise 2 which we had completed. I guess it's going pretty